Okay, folks, rounding out the ANOVA series, let's get into non-parametrics. So when we have violations to our basic assumptions, we have been taught that you need to have a non-parametric friend or equivalent procedure in order to still analyze the data based off of mean ranked information, as opposed to arithmetic math that we do with means and standard deviation. So instead of means, we're using mean ranks in order to determine that. So for the one-way independent groups ANOVA, the tool that we use is what's called the Kruskal-Wallis test. And the criteria for the Kruskal-Wallis test is that the dependent variable of interest has to be ordinal or continuous, so interval or ratio level of measurement, but the distributions for those dependent variables need to be in the general same shape. They don't need to be normally distributed, but the shape of the distribution should look somewhat similar between them. The real basic assumptions for a Kruskal-Wallis test are non-parametric equivalent to the one-way independent groups ANOVA, is therefore that the dependent variable has to be ordinal, interval, or ratio level of measurement. We assume that the independent variable or the grouping variable is nominal or ordinal level of measurement that has at least two or more, preferably three or more independent groups. We assume that the observations within each group are different, that we're not having any type of dependence happening there, and that the distribution shape is similar. So when I talk about how the distribution shape generally needs to be similar, I want you to orient yourself to the bottom left-hand side of the slide here, where you can see that you have the medians of data that is collected in some example data based off of race. And so you can see that the blue data is color-coded for Caucasian Americans. The red data is color-coded for African Americans, and the yellow or gold data is color-coded for the Hispanic Americans. And so in this case, even though the subgroups are different, the general shape of the blue, the red, and the gold looks pretty similar. And so when that happens and the distribution of each group kind of looks similar, then you meet the basic assumption that the distribution doesn't have to be perfectly normally distributed, but the shape is generally moving in a similar way for all three distributions. So that's what we're checking for with the basic assumption. For our hypothesis testing, we can then check our hypothesis test summary box, which we'll show you how to do in SPSS. And you can see here that we're given a significance value. And once again, the p-value is smaller than 0.05, which tells me that this is a statistically significant effect. How do I know that it's a statistically significant effect? Well, if I look at the bottom right-hand corner here, I can see that the p-value for that statistic is specifically 0.014, which is smaller than 0.05, which tells me that somewhere between three means, three or more sample means, or three or more mean ranked means in the case of a non-parametric procedure, that there is a statistically significant difference in the mean ranks of the data collected. And if I was to look at the ranks above the test statistics box, I can see definitively in an example with drugs that drug A with 20 people had a mean rank of 35.33, that for drug B of 20 people, the mean rank was 34.83, and in drug C of 20 people, the mean rank was 21.35. So the real answer to this is that if the p-value or the significance value, which represents the same thing, is smaller than 0.05, it means there's a statistically significant difference between the mean ranks of the data collected, which tells us that somewhere within these three ranks, 35 compared to 34, 35 compared to 21, or 34 compared to 21, are statistically different somewhere. And so that seems to make a lot of sense because 21 is relatively far from 34 and 35, whereas the difference between 35 and 34 is probably not statistically significant if we were to use our post hocs. So a common question people say is, well, Dr. Bruno, it's great that the Kruskal-Wallis test is the non-parametric friend to the one-way independent groups ANOVA, and it's great that my mean ranks are statistically different and I could still use my data, but how do I know to perform the post hocs? The way you would run the post hocs is by using a non-parametric equivalent that we talked about in lecture 4, which was the Mann-Whitney U-test, and that is used for independent groups designs. And so remember, when we want to compare the mean ranks of group 1 versus group 2, group 1 versus group 3, or group 2 versus group 3, we can do it non-parametrically with the Mann-Whitney U-test to make those comparisons among the tests. Yes, there are some limitations that when we do that, we may tax the alpha level 5% each time, even non-parametrically. But the pros is that we do have a Bonferroni correction procedure to correct for the alpha level, just like we do with parametric procedures. And so when we do a Kruskal-Wallis test and we find there's a significant difference, our non-parametric equivalent for the post hoc would be the Mann-Whitney U-test, which remember is the non-parametric friend to the independent group's t-test. So what about a repeated measures ANOVA? Well, for a repeated measures ANOVA, the non-parametric friend is what's known as the Friedman test. And the conditions that need to be met, or the assumptions for the Friedman test, is that our dependent variable is ordinal or continuous, meaning interval or ratio level of measurement. And our assumptions are that we have one group is going to be measured 3 or more times. Just like how in a one-way repeated measures ANOVA, one group is measured 3 or more times. So it's similar in that way and aligns really well. The second is that the group is randomly selected from the population. The third is that the dependent variable is ordinal or continuous in nature, which we said already. And the fourth is we assume a non-normal distribution. And so when we look at the data collected for our statistics, you can see that in a different example, I just pulled these SPSS outputs from my computer. You can see that in this case, there are 3 or more conditions, a control with nothing, a classical music, we'll call it, and a dance music. We had 12 people, so the same 12 people each got no stimulus, classical music, and dance music, and then you have the percentile data that's collected here. But when you look at the ranked data, right, you can see the mean ranks of 2.38, 2.17, and 1.46, and the asymptotic significance value of 0.022, 0.022. And so, because that p-value is smaller than 0.05, this tells us that the statistically significant difference is somewhere going to be between these mean ranks. But again, it doesn't tell us where those mean ranks are. And so the way that we perform those post hoc tests is by using, you guessed it, the Wilcoxon signed rank test, the non-parametric friend to the paired sample t-test. And we correct again for Bonferroni, which helps us to protect the family-wise error rate at 0.05. So the one thing that is relatively unfortunate when it comes to ANOVA designs is that we do not have non-parametric equivalents for factorial designs. And so if you violate the basic assumptions and you render that factorial ANOVAs are not possible with your data, your alternative would be to run things on a univariate basis using the two procedures we've talked about here. Your independent groups test, you'll run those separately. Your repeated measures test, you run them separately. You'll still be able to get some valuable information from them, but you won't be able to explore the interactive effects with these kind of procedures when the assumptions are violated. And so while the Friedman and the Kruskal-Wallis test are really helpful for giving us a path to analyze data that violate assumptions, they don't help us very much non-parametrically for factorial designs. And so in those instances, we just have to assume and we have to just come to grips with the fact that for factorial designs where our violations to the assumptions are known, we have to just run them separately. So we have to run the one-way independent groups ANOVAs with the Kruskal-Wallis test. We have to run the one-way repeated measures ANOVA with the Friedman test. But it gives us a number of options, and we can use post hocs with our non-parametric t-test to help us make sense of what's going on with the data when the data violate those assumptions. So I hope this video was helpful. We learned a lot. So again, practice makes perfect here. Make sure you're bringing questions to class, or if you're online, make sure you're contacting me and coming to my office hours if you run into any issues. If you have any questions, please practice. This is not something I think that you can learn in just one shot and be good with it. Repetition is the mother of learning, and that definitely applies to what we're doing, both content-wise in these lecture videos, but also practically how we're integrating them with calculations in class and how we're moving through our assignment. So thanks very much for your time and attention, and we'll see you all in the next video. Take care.